The research paper presents a novel theory of feature learning in deep neural networks, proposing a spring block model that accurately captures the dynamics and phase diagram of feature learning. The theory is based on the concept of data separation, which measures the ratio of variance within and across classes in each layer. The authors show that DNNs define a family of phase diagrams, where increasing nonlinearity results in increasingly concave load curves, with deeper layers learning better features. The study highlights the importance of an appropriate learning rate for achieving equiseparation and the role of nonlinear activations in breaking this balance. The proposed spring block theory explains why some DNNs are lazy and some are active, and how the distribution of feature learning over layers relates to test accuracy. The phase diagrams are universal with respect to various sources of stochasticity, including dropout rate, batch size, label noise, or learning rate. The research explores the dynamics of deep learning through a phenomenological model, inspired by the spring block system, which captures the interplay between nonlinearity, noise, and depth in deep neural networks. It reveals that a uniform load distribution, corresponding to a linear load curve, yields the best performance in terms of test accuracy. The authors argue that deep learning theories can benefit from both bottom-up and top-down approaches, drawing parallels with fields like physics, biology, and economics. They demonstrate that their phenomenological model can provide valuable insights into feature learning, an essential aspect of modern DNNs. The study also reviews various works on neural collapse, data separation, and feature learning, highlighting the importance of considering depth, nonlinearity, and noise simultaneously. The authors suggest that their model can help guide training to find better networks and improve generalization, and that it may lead to exciting connections with other areas of research. The authors delve into the phenomenology of neural networks, examining it through the lens of regression and the spring block system. In regression, they define the load as the mean squared error of the optimal linear regressor from the LTH layer features, denoted as DL. This load exhibits a convex curve under noisy training and a concave curve under lazy training, as depicted in Figure S2. The spring block system is introduced as a second-order system, where the force flat is rewritten to incorporate friction, resulting in equation 9. The friction fluid depends on the force Fl and velocity xl, with three distinct cases: sliding friction-resisting movement, static friction compensating for other forces, and zero friction when the block is stationary. This is summarized in an activation-like form, sigma, z, x, in equation 10. The phase diagram of this system is presented in Figure S3, showcasing the load curves and elastic potential energy. The authors discuss the noisy equilibria and separation of timescales in the spring block system. Without truncation, the trajectories exhibit two stages: an initial stage dominated by the elastic force and a later stage where the spring force is balanced with friction. To avoid this, the authors propose three methods: assuming bounded noise increments, applying noise decay, or introducing a stopping criterion. An alternative formulation of the spring block system is presented as a second-order Langevin equation, where noise is added to the velocity independently of friction. This results in equation 11, which can be solved using standard SDE integration. The phase diagram of this system is shown in Figure S4, demonstrating similar behavior to the original formulation. The authors emphasize the importance of noise decay to ensure convergence in this formulation. These pages illustrate the connections between neural networks, regression, and the spring block system, providing a deeper understanding of the underlying dynamics and their implications for deep learning.